The self-driving space has been an interesting one to watch. For years, companies like Uber said we were headed for level 5 autonomous vehicles, ones that could operate in essentially any condition with no human oversight. But getting there has been difficult. Today's guest, Drago Anguelov, thought that it was too early to get into self-driving for a while. Eventually, he ended up at Zoox and later at Waymo, where he is now distinguished scientist and head of research. Over the years, Drago and his team at Waymo have done a lot of important research pushing forward autonomous vehicle capabilities. Today, Waymo has riders in fully autonomous vehicles 24/7 in multiple cities, producing valuable data to improve their technology further. There is still a lot of room to run in this space, and many exciting advances remain to be seen. This is the Gradient Podcast. I am your host, Daniel Bashir. If you aren't already subscribed to The Gradient, go ahead and follow us wherever you're listening to this podcast. You can also follow us on Substack, where you'll get notifications whenever we release a new podcast episode, article, or newsletter. But now, without further ado, Drago Anguelov. As you're in the position of leading research at Waymo, I am hoping we can use this opportunity to give the listeners a little bit of a taste of what's going on in self-driving right now. But I do want to start, as always, at the beginning. How did you get interested in AI and self-driving in the first place?
Well, pleasure to be here talking to you. And indeed, autonomous driving space is currently very active. There is a lot of things happening. We'll be happy to talk about it. I got into the AI space in 1997. I was an undergraduate student at Stanford, and there was a AI class that a roommate of mine had taken and said it's the hardest class he ever took by a new professor called Daphne Koller. And it was so hard that maybe it was the first edition she ever did of the class, and some homeworks didn't work, and he tried all night to fix it, and it just made this impression. Like, that's an interesting class. It made a mark on my friend. And so I took the class in 97. And I would say that that was very foundational for me because that class got me into the field and also got me interested in doing research with the professor who was teaching it, Daphne Koller. And later, I ended up doing a PhD with her. She was my advisor. And so it was quite definitive class. One other thing I remember about that class is that quarter, I took 4 really difficult classes. And one of them was operating system, which was known to be hard. One was this one. There was some other computer science theory class and one more class, and which is a lot at Stanford for a semester. And I remember I had to take the final for this class, and I tried to solve the final for 6 hours until 1 a.m. And then I'm like, I barely solved anything, and I'm just going to sleep and wake up and whatever happens. And I just happened to be lucky and, solved enough problems where I guess Daphne Koller did want to work with me in the end, but it was very close to not happening. So it was very dramatic all around. And here I'm still in AI. What is it, 26 years later?
Life seems to work that way sometimes. Was that class probabilistic graphical models by any chance?
First class is 227. The one that really I stayed all night was probabilistic graphic.
Could you tell me a little bit about how that evolved into the set of focuses you had during your PhD? So you were on some really interesting papers, especially the single-shot multi-box detector, and I'm kind of curious how your interests evolved.
So that paper came much later, right? So if you roll back in time, I was doing my PhD starting in 99, 2000. And at the time, deep learning wasn't that popular. Honestly, graphical models were very popular. My advisor, Daphne Koller, was one of the people that did quite a few seminal advances in the field, and she was doing graphical models applied to many different disciplines. So there was dynamic Bayes nets for temporal series modeling. There were what was called PRMs, probabilistic relational models. She was applying things to natural language processing. There was game theory, and her field, the most popular she was doing was bios. So I was exposed to all of these, but I was actually her first student who did perception topics. And so I joined, and I initially was going to do a PhD with a computer science professor who unfortunately didn't get tenure. And she decided to try, well, with me to do some perception. And soon after that, she met Sebastian Thrun at CMU and sent me there to his lab to collect data because he was the one with robots and Daphne didn't have robots. So that's how started the collaboration also I've had with Sebastian Thrun. That said, in those days, right, deep learning was not popular also, but what we used to do is probabilistic graphical models, Markov random fields, Bayesian networks. We could design reasonable, how to say, probability independence assumptions about the domains we're solving, and they were improving things compared to vanilla classifiers. And that's some of the things I was working on, only I was applying it to lighter data or depth data. And so some of the applications I did is, okay, well, if you're mapping an environment and objects move around, can you tell which objects moved and where did they go, right, automatically? Or if you have a body and you see it in many different poses scanned, can you figure out what is the articulation of this body? Or if you have a shape that someone moved a bit or like deformed a bit, can you register to shapes like this almost automatically, or how far can you push it? So that's where trying to apply ideas from probabilistic graphical models. And so all of these things, after I did them, it kind of culminated, okay, let's try to model the human body. So that was the scape work at the time. This is 2004-5. And that was my only foray into computer graphics until recently. And it lasted about a year, but there we invited a bunch of friends, scanned people in there used to be this cyberware scanner, you stand in it, and you stand maybe for at least 30 seconds, if not more, and it scans you. It goes, and there's a little platform that goes top to bottom and scans you with very high accuracy, maybe up to a millimeter or two. And so I scanned a bunch of friends who I convinced to come. I scanned myself in a bunch of poses, and I used machine learning to learn a deformable human model, which for its time was a relatively novel topic. And that became that paper, and that was the end of my PhD, a little bit combining all the things I did, right? But after that, I went into computer vision, right? So that maybe the seg to detectors and SSD and Inception and so on. There's a lot of stories. Essentially, after doing this 3D type of perception, I went to a computer vision startup, and it was called like.com. And we used to do visual for shopping, and at the time it was still novel face recognition and organization of photo albums. We used to work on that too. So I did some technologies like this, computer vision. StreetView, I worked on pose estimation of the platforms. We had even boats and trikes, and there was, I think, snowmobile with the StreetView camera on, and backpacks. And my job was to try to get the pose from all these devices to be good, which used actually also some camera structure from motion, computer vision actually in its time we used. And after that was around 2010, I went back to computer vision, and we started looking at recognition of objects in photos. And initially I started still with, at those days, it was still pre-deep learning. It was 2010 to 2012 or so, 13. I was working also on probabilistic graphical models. So we would train these models. It's called deformable parts model. You have these little histograms of gradients, and they have certain shapes, and you define these templates that you train on how they deform, and you train them. They're support vector machines, but a little more structured than this. And so I had a system like this at Google that did, for its time, state-of-the-art pedestrian detection and car detection and a few other special objects that have a lot of these oriented gradients, because a lot of them don't. Those we could not do. And AlexNet came, right? And then your world turns around and you say, okay, actually for everyone at Google, around late 2012, AlexNet was the first neural net architecture that was really good. So we had others before, but they were not that great. Uh, they were not very performant, were not even convolutional, some of them. And we were trying the classical methods, and they were largely competitive with these deep nets. And then AlexNet came in, and all of us looked at all our systems and said, uh-oh, our systems are not competitive with this thing. And so now it's a new age, and we need to figure out how to do all these tasks that we want to do, but now with deep nets. And so I got into this early 2013, and then we started training deep nets. And a lot of this, now that deep nets were working, it was clear that photos is a great application. And so my team, it was like between 4 and 10 people, and a sibling team, which still I think works on this, at Google, we joined forces and we started training and inventing the backbones, the neural net architectures that would run in the Google stack, annotating every image that comes in. And so we went through many generations of these architectures. And initially, these models were classification models. And you can see some papers out there by our team, Christian Szegedy, who invented the early architecture. There's all stories about all of this, but there's one called Inception that was popular at the time. Inception V1, V2, V3, I think there's a V4. And then there is Nexception, and there's a few of these that came out. And these were born out of our experiences trying to make larger and better structured models than the simple AlexNet that we started with. And they were classifiers. But soon after that, after we had pretty good classifiers, it became clear that we want to do object detection. Because it's reasonable when you have photos to also want to know where the objects are. If you can detect them, you can zoom on in and zoom on them and do even better job in many cases. And so in parallel, I started an effort to try to push object detection capabilities with deep neural networks. And again, our team and Christian Szegedy again, Dumitru Erhan, and a few other people, we developed some of the first kind of neural net architecture that's a pure architecture without necessarily heuristics or intermediate stages to what we would call single shot the detection. So you take the full image as input, and out of your network come all these detections. And so SSD was an example of these types of models. I think before that, what was popular, because that's how computer vision algorithms were working, is you start with the image, you have some operator that gives you a bunch of regions, and that's based on some clustering of textures and other things, and or superpixels or other things. And you take these regions, and then you classify all these regions, maybe 2,000 candidates, and then you say which ones are the right ones. In our case, we wanted to just plug everything into a neural net, and the output come out. Right, with a single stage too, because sometimes the neural net can produce some boxes, and then you can zoom in with these boxes, pick results, process further. We wanted it single shot, right? So that's the models we did. They were the fastest. There was a reason why we wanted such fast detectors, actually. So at Google at the time, this was early 2010s, we ran neural nets on CPUs. So they were slow, and we wanted to have as streamlined of a setup as possible, because neural nets on CPUs take very long time. And so SSD came out of these considerations, right? But in its own time, it had reasonable design. Some of the decisions with anchors, so you need to discretize the space. So we had these anchors that tile the space of outputs and sizes that you can have. In its own time, that worked reasonably well. I think now it can do even better, but it was one of the first, along with YOLO, single-shot detectors that were very performant.
Yeah, I remember this because before that, I think faster RCNN and its Oak were kind of the state of the art, and two-stage detectors seem to be winning the day. Now for one stage, it seems like RetinaNet is kind of the basic one that people are going to a lot.
Yeah, and that one was an improvement on what we had, but I think in our time, there was RCNN initially, fast RCNN, faster RCNN. These are all two-stage detectors, and still, in a lot of domains, two-stage detectors are better in quality, but they can be significantly slower. And so we always wanted to have the single stage, and I think a lot of industrial applications benefit from the speed. And so I think single stage is still here to stay.
Right. So, kind of moving from there to your current time at Waymo, this isn't the only self driving company you've worked at. You had previously worked at Zoox as well. And so you've kind of been in and around this space for a while. And I think looking at self driving from the outside, many people have certainly felt like there was a lot of overhyping at the beginning that I think many people kind of bought into as well, that we're going to reach so-called level 5 autonomy very, very soon. And I think a lot of promises were made, and I think that the researchers in the field, the engineers, people outside of it, started realizing, wait, this is actually quite a bit farther away than we initially anticipated. And I'm just curious, as somebody who's been really deep in the field and working on it since, quite a while ago, what your experience with those expectations was.
So I'll tell you, mine is a bit interesting because it started in 2005. I was at the Stanford AI lab trying to finish my thesis and potentially afterwards go to a startup. And Sebastian Thrun was doing the DARPA Grand Challenge. And so I saw the team work on the vehicle, and it seemed an exciting challenge, but it also seemed quite heavily engineering challenge at the time and a bit of a demo setup, right? I mean, you're competing in this very early task, I mean, in maturity. And I did not participate, right? So I said, no, I'll finish my PhD. Later, I joined Google. And in 2009, Sebastian Thrun started the the Google self-driving project, right? And around that time, I had an opportunity to reach out to Sebastian and say, hey, I want to do self-driving, but I didn't, right? And why didn't I then? Again, to me, it's like, well, it's still so early in this space, right? It's still very much in the demo area. It will take at least a decade to get to good performing vehicles. And I was working on StreetView at the time. StreetView was a new product. There was a ton to do and improve. And we were doing some really interesting work with essentially, well, making good data for StreetView. And the way to make good data is you pose all the auto photographs really accurately everywhere and cross-reference all the runs you have, and you're able to reconstruct a reasonable 3D geometry so it can be navigated and used. And you have these virtual worlds of sorts that you can attach various virtual reality tags and other things. So I was working on that. And so I missed the start of the Google self-driving project. It seemed to me that that project will take many, many years, and there's time to join at some point. And then when deep learning came, 2013, 14, some people in Google Brain actually started working with the self-driving car project. Some folks I knew there reached out and said, hey, do you want to join us? And then I was still not ready. I'm like, well, we're still only figuring out how computer vision works with deep learning. Self-driving car is a whole other level. Like, let me get a feeling that computer vision can work, and then we'll think of self-driving cars. And so that lasted me until 2015, so almost a decade or more, where I did not get into it because it seemed too early in some sense to really work for me personally. Then around the end of 2015, I started thinking, these computer vision models and architectures we build and detectors and so on, they really work. And before that, in the early days, maybe in 2009, when the self-driving project was starting, a lot of the technology is based on things like Sebastian's probabilistic robotic book, right? So you take the LiDAR, you maybe build segments out of the LiDAR, you start tracking them. Then with these tracks, maybe you can predict reasonably how they go with some semi-heuristic models. And then you add some controls and drive around these things, right? Like that was the technology of 2009. In 2013-14, deep learning started coming into the spot, but only in 2015 I said, you know what, this deep learning thing, we understand it, it's here to stay, we know how to do well things, computer vision. If you have good computer vision, a lot of the same ideas you can apply to LiDAR. At that time, LiDAR was still not very well understood with deep learning, at least externally. It turns out when I joined Waymo, Waymo understood LiDAR pretty well with deep learning earlier than I would have anticipated. But, us on the outside, not quite yet. But in 2015, I said, okay, we can get the handle of LiDAR. And once we have good perception representations from camera and LiDAR, then we can do prediction and planning on a good representation of the world that's rich and detailed, and we'll figure out how those model works too. So end of 2015, I'm like, you know what, these self-driving cars will work at this point. I think we have the key technology. To me, I'm biased, right? I'm a machine learning person, so to me, deep learning is a key technology to enable self-driving or autonomous driving vehicles. I said, okay, time to get into the space, right? And so that's when I got in. So it was around December of 2015, so almost 2016. And yeah, and it's been quite a ride since. I think every year or two, there's dramatic improvements in our space. And now you can see there is actually companies out there with providing service in some reasonable scopes. So it's been a wild ride, and it's continuing. Yes.
I think this is a good place to transition to the beginning of the particular wild ride you've had with Waymo. And I think perhaps a place to begin with this is you have brought up a set of the kinds of problems that people encounter in self driving, prediction and planning, for instance. For somebody who maybe knows about ML but isn't as particular with the suite of challenges faced to make a self driving system work, could you give a brief introduction just to what that looks like?
So there are several questions a robot, and in our case, an autonomous vehicle, needs to answer in order to be able to, well, fulfill its mission, right? One of them is it needs to know where it is because its job is to drive people or goods places. So you need to say, drive me over there. You need to have some notion of a map in which you can plan some kind of routes to get you to a destination, right? So you need some systems to position your vehicle quite accurately in the world on some map. Now it can be Google Map style map, which is low fidelity, suitable mostly for routing. It can be a richer map that tells you a lot more about the world as well. So you localize to this map, and it gives you some prior about the environment, but now you need to perceive the environment yourself and form a world model of what this environment looks like. And so that's the task of the perception stack. And currently there is different companies use different sensors to achieve this. I think the most popular sensors are camera. Everyone's familiar with this. LiDAR is also a very popular sensor. And I think the first one that, Stanford, say, self-driving project started with cameras, but added LiDAR quickly and grew from there. I think Waymo and its Google self-driving project, earlier incarnation, started with very heavy initial focus on LiDAR. So LiDAR is an amazing sensor. Within certain distance from the vehicle, it's maybe the most powerful. It shoots this very targeted beam of light and sees when the light comes back, and that measures, the distance to things, and also potentially you can get some information about their intensity and other properties. And if you can do it at high resolution, it just draws the world for you in 3D, and it's really easy then to not hit things that are there, right? And it's a very high information sensor for per beam. In general, if you want to do 3D perception, especially short to mid ranges over 100 to 100 meters, LiDAR is hard to beat. It's very powerful. And the last sensor is radar. Radar, in each of these sensors have very different strengths. So camera is the highest information content, the most pixels. LiDAR has amazing estimation of shape and depth, and essentially see things when they're there. Radar is really good at bad weather, very long distances, and you can estimate velocity, longitudinal velocity relative to you because of the Doppler effect in radar. So all of these taken together is extremely powerful combination, right? And there's, of course, questions, can you do subsets in various ways? We use all three. There's other sensors people use. There's sonar for short distance you can put on the vehicle. Some vehicles have it, and robots. There is also thermal cameras and so on. But I mean, eventually it starts accruing quite a lot of complexity if you put too many different sensors. I think so far a camera, LiDAR, and radar are the most popular in the stack, and then some companies differ, right? And so you take these sensors and usually see 360 around you because you need to have situational awareness. There's a situation where things come at you from all directions, right? And so from these sensors, you build a model of the world. And this model of the world is, here's all the pedestrians walking around and how they're walking. Here's all the vehicles. Here's their blinkers. Here's the traffic lights. Here's the signs. Here's the road markings. All of this you can process. And you can compile from all your sensors into a world representation. This world representation, now you can do prediction and planning. So we get to the next step. So you see the world. The world has static objects. Those you perceive, don't hit them. But there's a lot of actors in the world. There's pedestrians, bicyclists, you name it, skateboarders, even segways. There's people on horses, right? So on, people walking dogs. You need to understand what they're going to do, what they're going next, because that affects you're planning. You don't want to go and hit these agents, and you don't want to cause them discomfort. So you need to anticipate what everyone is going to do. And that's called behavior prediction, right? So that's traditionally will say, okay, do perception, do behavior prediction. And then in this world, when you know roughly what is likely to happen and where everything is, you do planning, you plan safe paths in this environment that take you to your goal. So that's roughly the vision of the stack. And there's one more piece that's very important in autonomous driving. Ultimately, how do you test this stack? Well, you can drive with safety drivers, and that's great. But ultimately, a lot of these events happen once every hundreds of thousands, in some cases, and millions of miles in others. You want to replay difficult situations, not just drive them every time and hope you encounter them. You want also repeatability. Simulator is a great tool. Ultimately, you want to test your stack in an environment over time, do the decisions amount to good performance, right? So that's the purpose of the simulator. So simulator is a key piece of the autonomous driving stack. It doesn't necessarily sit on the car, but it's a core part of the things that you need to build. So these are the main pieces. And I think there's been one evolution recently. So in our space, people stop thinking of behavior prediction and planning as separate components as much. They're highly dependent on each other. So now you just say behavior modeling is maybe one interconnected component. And why is it interconnected? Essentially, well, you, by your actions, influence what others do. So you can't just predict what others do in a vacuum, independent of your actions. It's a bit of a chicken and egg problem. And so when modeling, you have to think about it. And ideally, you want to think of it in an interactive way and not what is a priori everyone going to do. Let's avoid anything they could do that can make you too passive, right? Because now you're not taking into account their reactions to the things you do. Maybe you forbid yourself too many possible things, right? So that's maybe one evolution. But these are the core pieces: mapping and localization in the map, perception, behavior modeling and planning, simulation. And that makes a robot that one can experience now in several cities. And I would say that compared to most robotics domains, autonomous driving, one of the most distinguishing characteristics is it's a multi-agent planning problem. So you're in this rich, complex environment, and you're interacting with humans in this environment, and you need to negotiate with them and anticipate what they're going to do. Most other robotics tasks do not have this type of interactivity, at least to this extent. Even when you have a small robot that's an arm and moves, it usually moves slowly. You have time to get around people. A robot in the hallway, still, you can just move slowly and get away of the most out of the most complicated interactions. For us, you really need to attack the problem head on, and that makes us unique. Of course, there are humans operate in this way when we walk around as well. But autonomous driving presents this interesting multi-agent problem, which is different than the standard problems you normally see.
Yeah, and a unique set of problems for generalization difficulty as well. I want to start digging into some of the approaches that Waymo has taken to tackling different parts of the stack. And where I want to start is in a previous conversation I had with Stuart Russell. He commented that Waymo's initial approach to the self-driving problem was, and I'm quoting him, even more old-fashioned AI than he would have recommended. And I think this speaks to the kind of suite of methods people have tried to use to start tackling problems that kind of go from end to end deep learning to more mixed methods that are integrating more symbolic ideas as well. And so I'm curious what the state of that was when you were getting started at Waymo, and perhaps how you've seen their approach evolve. And perhaps if you could shed any light on his comment there, if you happen to know about what some of those early approaches looked like.
Do you know what years he was referring to? Just
I'm actually not sure. I think when he says early on, I assume he means probably at the very beginning of Google self driving, but he didn't specify which years.
so I think when Waymo started, which was Google self-driving car project, that was around 2009, and it was also started by Sebastian Thrun, who was a kind of mobile robot expert. Um, I think in those days, Google deep learning was not a thing, right? Machine learning was a thing, but we typically would design a bunch of features and apply a linear classifier on top or SVM. But if you had to do kernels, they becomes quadratic, so maybe too complicated. But at least linear SVMs and a logistic regression, these were kind of models of choice, right? So that was the technology of the day in 2009. And so a lot of the things that you start with, and generally, actually, in machine learning, this always happen. You start with the best heuristics you can come up with. And that's an engineering approach, right? So you can say, okay, let's build the simplest thing that could work, learn what are the shortcomings, and build from there. It used to be my impression that's how Sebastian Thrun liked to operate. Daphne Koller would operate in a very different way, actually. So I was a student of both, so I get to observe the opposite view. Daphne's like, what's your model of the world that is good? Let's approximate it with probabilistic graphical models the best we can, and let's run those, right? So she was a bit more top down in thinking, and Sebastian was very bottom up. So it was very natural that the technology in those early years was starting, let's put the system together, let's use the current technology, which is LiDAR, segmentation of LiDAR, tracking of the segments, and then some prediction, maybe heuristics for prediction, and then some planning, which of course you can use control and other things, right? I think that's my expectation of what it was. I wasn't at Google at that time, so take it as a speculation, but I think a lot of the stacks had this kind of flavor. Now, deep learning, I know for a fact after joining Waymo, I joined it in 2018 in the summer. And so 2018, after having been at Zoox, Zoox was it still is, not a startup anymore, though it's part of Amazon, your company. Zoox had started in 2014, and I had joined that company. I was leading the perception team at Zoox, so I had an engineering role there. We were building the perception production system. And in that point, deep learning was somewhat established, but for a fact, I know that, and I found it when I came to Waymo. Deep learning came to Waymo reasonably early, and it came actually through people like Ilya Kryzhevsky, Alex Kryzhevsky, who is the author of AlexNet. He worked from Google Brain. He started working on problems for Waymo, and there was some really exciting early deep learning advances he brought about. And there was some really sophisticated deep learning processing of LiDAR, for example, that Waymo had way ahead, way before anyone had it, right? Now in 2018, when we came in, my mission, so I came in into the summer of 2018 from Zoox. And my mission was to help with machine learning at Waymo. And I inherited a team, a start of a team, 5 or 6 people. And we started building on it. And the mission was, let's try to push machine learning for autonomous driving. And let's have a team that is machine learning experts, that we believe that machine learning and deep learning specifically is a key to scaling and developing the scalable solutions that we need in our field. And I'll maybe say in a couple sentences why scaling is so important in our field in a second. But we started building this, right? And a lot of our work has been, how do we apply the state-of-the-art machine learning trends and solutions, architectures, models to our domain? And this is to all the systems. So we started, there's typically in robots, like deep learning first came in NLP and perception, or speech recognition even, but it comes to perception, And then it came to behavior prediction, planning, and now it comes to simulation and evaluation, right? So all the fields of Waymo today are extremely heavily reliant on machine learning and deep learning. And I would say that we are a machine learning primary company. If we can solve things with machine learning, we prefer to do that. Generally, this is beneficial because in our case, and I think you alluded it, right? Why is autonomous driving difficult? Well, it's a complex multi-agent environment. Also, there's a ton of different things that can happen. So the amount of things that happen in the real world when you drive is huge. And you need to understand all of these details. And it's very hard, and I think Stuart Russell was alluding to this, it's very hard to encode all these things by hand. So as a human, right? And what we instead have is we have this rich data that we observe by driving tens of millions of miles in the real world, and we also drive tens of billions of miles in simulation. You get all these learnings. These learnings, machine learning lets you translate them into rules and ultimately decisions that you can then validate with humans, but it already narrows down the things you need to think about, right? And code by hand. And so it's a huge scaling crutch. And I think a lot of these problems of getting the vehicles out there is related to this type of scaling. We have to handle this wide range of things that happen, and we don't have enough humans to encode enough rules. And so that's what we have been pushing, right? And this continues. I think now, interestingly enough, the technology continues rapidly evolving and new types of possibilities and models occur. And ultimately, the trend now is to have these big foundation models. Models become larger and larger and more powerful. And so ML over time takes bigger and bigger part of the stack. Now, that said, our stack is not an end-to-end neural network. There's good reasons for it now, but there is a trend to have fewer, more powerful models, and you need to be very thoughtful how you design the stack. There's specific properties of our domain that one needs to be thoughtful about. You cannot just take vanilla solutions often and directly apply them, and that's partly why we need a team that is an applied research team that can balance the trends with the realities of your own domain.
Let's start cracking open that box a little bit. And I'd like to begin perhaps at the start of the stack. One way I think we could organize this a bit is you gave a talk at ECCV 2022 on scaling 3D detection to the long tail, where you detailed some of Waymo's research contributions to these areas. So, for example, you worked on sparse window transformers for 3D detection and point clouds, a number of other techniques for things like data augmentation. Could you walk us through a few of the particular challenges that you were facing up against there, and then perhaps some of the deep learning architectural innovations you were making and solving them?
So in perception, the challenge is always what is the right architecture. Different architectures have different scaling properties. Also, we want highly performant models that can run on board. And so SW Former is a research example of such an architecture, right? As you guys probably know, in terms of quality, performance, transformers are very popular today. And our experience also has been that as we add transformer layers to models we have, performance typically improves, right? But the challenge is, okay, let's come up with a neural network architecture that is suitable for our domain, that's really scalable, right? So that's research I presented. SW Former is one model like that. And then let's start scaling it, right? So what does it take to scale models? It is architecture and data. And data is essentially, you need to have this machine learning pipeline that you start, create a model, evaluate it, find potential issues in the model, go find more data, right? Collect more data, label more data if needed. Ideally, don't even label it, auto-label as much of it as possible, and then repeat the circle, right? And so a lot of our research is, okay, one of them is architectures, and second is data. And around data, there are several key areas. For example, one of them is data augmentation. If you know you're dealing with objects, you can define a set of reasonable deformations of these objects in LiDAR, and in images, you can also define a set of scalings and shearings as well. And if you apply these deformations, augmentation, if you train a larger architecture, right, as well, because now it needs to learn more things, you can significantly improve the quality, right? And it's a standard trick we've always used from the early days, data augmentation. But in the richer it gets, the more structured data gets, and lighter data is quite structured. You have this big space of possible augmentations. And now the question is, well, how do you find the right settings for all these? It becomes a chore in itself. And so one of the works I presented is, or it's really a series of works, is how do we effectively tune these knobs to get a good set of augmentations. So for given a certain architecture you have, there's a certain set of optimal settings for how much you should augment. If you augment too much and the architecture is small, you hurt the performance on the actual examples, right? Now, if your architecture is large and you don't have enough data, you want to turn on the augmentation more. And so we had research on an algorithm to do this, right? Now, the augmentation just takes the existing data and tries to do these perturbations. You can go a lot further and say, okay, in our domain, what happens is we drive an environment and we observe the scene from the past to the future in practice, right? Over 20 seconds. So now, given all this data over time, you can go and reconstruct what happened in the scene with really high precision. Why? Because you see every object up to 10 seconds and possibly from all possible directions for over this time. And over all this time, then you can, if you average your knowledge from an observation from all this time, you can get dramatically more accurate estimates. And once you have them, that labeled your data. Now you can train your, because now you just take raw data, you run this outboard perception, no human labelers, nothing, right? It produces you all kinds of labels. Now you take these labels and you can ultimately train your model with them as well. But you didn't spend cost on labelers, you just turn the wheel. It's mostly pipelines running. So we developed a framework to do exactly this, right? And this was one of the works I presented. Now, this framework breaks down, though, in the case of most rare examples. So if something is really rare and you want to track it accurately, right, and segment it, at some point, it becomes too difficult too, because you have too few examples of this. In those cases, you still want to use humans to label it, but then the problem becomes, can you identify these cases that humans are needed? Because for most of them, you don't. And so now we also did research to identify those cases, right? So here is a set of 3 or 4 techniques that make the data scaling dramatically easier to the rare examples than maybe the vanilla setup you start with, where you just send a bunch of scenes to the raters, right? And so now you can develop your models dramatically faster, because ultimately you want these examples on the rare cases in your training set, right? And this is a way to effectively produce and focus on those. So these are a set of works that I presented, right? But they illustrate how to make a performant MLOps type of setup for our case.
The next set of challenges that I think are kind of appropriate to focus on are, again, drawing from one of your talks surrounding the idea of behavior models. And in this, we're now concerned with how do we make decisions when we're in this multi-agent environment? How do we model the interactions of things between us? And you kind of have this set of very hairy, complicated problems. And in the midst of all this, you introduce some innovations like Waveformer, for example. Do you think you could introduce us to some of the particular things that you have introduced, both at the time of that talk, but then perhaps since then in this area?
So this is the area of behavior modeling, right? And currently, you can maybe think of it, and it doesn't have to be treated separately. I mean, one can do a model that spans both, but at least as presented and as focused, you can think of there's a perception model that takes several lidars and maybe cameras and makes a model of the world. Typically, the model of the world we make is something that fuses information from many sensors. And each sensor has certain position orientation, gives you data typically in some perspective projection space. When you fuse them, you want a common space ideally for all these sensors, and that's typically in our domain bird's eye view Euclidean space, and it works at least up to a couple 100 meters or more. It's a good way to go. In some volume of the car, 200 meters and around, you collect what's practically top-down representation. The world relative to driving, there are things on the road moving around. It's 2D in a sense. So you have this top-down view. There's objects moving around. There is a bunch of lanes and signs and things, but you can all represent it in this top-down Euclidean space. So we represent things in this top-down Euclidean space, but a lot of them are reasonably sparse. I mean, also we're looking up to hundreds of meters out. It's an extremely large space. So SW Former can take the sensor data and produce objects in that space and potentially semantic segmentation signals and other things in Euclidean bird's eye view space. Then the behavior model needs to take it all and predict things like futures for ourselves, futures for likely futures for the others agents in the scene, right? And now there's two ways, and that's what Wayformer is. It's an architecture that now operates starting from this intermediate representation and models behavior as well. Now in autonomous driving, there is a very interesting twist. I mean, I'm originally a perception person, right? And a lot of the machine learning models that we most understand and know how to do is a type of classifier or supervised setting where some input comes in, right? You process it, some input comes out, and that's your task, right? Now, autonomous driving and generally robotics, it is tested in closed loop, meaning you generate a policy, something that drives the car, right? And this policy that drives the car runs step after step after step, generating an outcome potentially that can take tens of seconds. And then you evaluate what happened, all right? And so now the question is, how do you deal with this modeling? There's many ways to model long-term futures. Also, they tend to be exponential in possibilities. If everyone can do many different things, you put 100 agents in the space, how many futures are there, right? And so some of the work I present is, well, you have an architecture to take in the world. It's a transformer architecture again, right? There's a pattern. It's performant for its own setup. And with this architecture, we can predict, for example, independent futures for every agent. That's the classical task. So you say, oh, every agent, for example, gets, give me 6 likely futures for this agent, each with its probabilities and some uncertainty of how likely it is to be close to this future, or is it maybe diffuse possibilities around that path that you can generate. So that's an example. So every agent, for example, give me 6 most likely futures for each agent, because agents are non-deterministic, right? It's not like only one path to generate. You can maybe anticipate 6. So that's an open loop way, like a single shot. You have a past of 1 second. You predict the second, the future, say, up to 8 seconds. That's a problem task we have in our Waymo open dataset challenges, which may hopefully get to discuss. And so your task is to do that, and that architecture does it really well. Now, there's many extensions to this that are possible. We can predict futures for ourselves and dependent futures relative to each of the one we do for the other agents, right? So that's one paper. But all of these, if you just think of it, 1 second history comes in, an 8-second future comes out, you can do things like this. Right? So that's one class of model, and I present in my talk. Where it gets really interesting is when you start to think of it as an agent and as a policy. So you produce a future, you move on this future, then in the new step you produce another future, and you move there. And now the question is, okay, well, will it work well if you do this? You train to match the futures, and you just open loop, and then you test closed loop, and everything works, right? And it doesn't quite work very well. And the reason is there is this known problem of covariate shift, and there's an algorithm called Dagger that actually Stefan Roscho is now at Waymo. It's a seminal paper from CMU in 2010, right? He developed. So you need to potentially train these policies to be robust to covariate shift. And to train them to be robust to covariate shift, you either need to add heuristics and human constraints, so you need to do some closed loop training or imitation learning beyond behavior cloning, which is the well, something comes in and a one-step solution comes out. And so then a lot of the research we're presenting is on different forms of this closed loop training. And there is two approaches. I presented at Coral, which is also a talk you can see at YouTube. One of them is just pure imitation learning. So you train essentially policies such that if you apply a discriminator on the futures, it says, well, you generate futures that look like the stuff I've seen. So that's one type of imitation learning, right? It trains closed loop the policy to stick to states it's seen, which is a good property. It prevents you making small errors every step and accumulating a lot of error. Then you off the data manifold, you see things you've never seen before, and then these models can predict, somewhat arbitrary behaviors, right? So you want to stay on the manifold, and closed loop training keeps you, and imitation learning is one way to improve behavior cloning. Another way is reinforcement learning, right? So we presented also a study of how imitation learning and reinforcement learning for our domain compare. What do you do when you have one versus the other? What are the properties? What kind of behaviors emerge, right? And this is some interesting research work. Of course, it's done on a fairly simple world with box agents moving around with fairly simple perceptual representations. There's a lot more to do, right? I think ultimately you want to enrich the world in the simulator and apply similar techniques there. Now, the last thing I will say is that in our domain, you need to build your own simulator as well. Why? Because a lot of the well, first of all, you need the sensors to be realistic and other things. And nowadays, machine learning can be quite good at this. And second, you need the behaviors in your simulator to be realistic because you're playing out scenarios. And these scenarios depend on essentially, as you make a decision, others react to your decisions. And if they react unrealistically, you'll draw the wrong conclusions about the outcomes of your decisions. So then you don't have a good evaluation. And so you need to develop models of the behavior of others as they respond to you. And so that's an entity called sim agent. And we build this sim agent. It's an interesting task. Actually, again, we just today launched our 2023 Waymo Open Dataset Challenges. It's fourth annual edition. For a fourth year straight, we have 4 challenges. And one of them is on sim agents. So that's a new challenge, and we invite people to try to help build simulated agents who behave similar to how humans behave. And we provide, of course, data, 100,000 sequences showing you how various vehicles and pedestrians behave, and ask you to build such models, right, with machine learning. So that's exciting. I look forward to what people will do with that.
In planning, you had this really interesting approach in your imitation is not enough paper, kind of combining imitation and RL. I am just curious if you or your team at Waymo or anyone you're aware of is starting to explore distributional RL in a self-driving context.
So it makes sense to do, and I think a lot of it is also distributional RL, depending how you define it. But I mean, at least the agents, you want to be distributionally realistic, right? So you want to, like, every scene can end up a variety of ways. But if you look at the distribution of behaviors, you want somehow to match the observations in the real world as a distribution of behavior. So our metrics are a little bit like this. I think generally reinforcement learning is people do work in our domain, but I think it's still very much a work in progress. I think it's tightly coupled to how good the simulator you can build, because reinforcement learning often requires you to play action forward for a long time before you see the outcome. And in that case, the simulator realism needs to be very high. And so we constantly work on the realism of our simulator. And then the more it is true, the more we apply RL methods. And you can see us publish some RL methods. So it's certainly top of mind for us. But it's a very active developing area of research and generally in our space.
I think this is a good place to start closing up, and where we can perhaps begin with this. You mentioned the Waymo open dataset earlier. Perhaps you could give a bit of an introduction about the inspiration for that and the impacts it's had for Waymo and the broader self-driving space so far.
we started this work soon after I joined Waymo, and many of us, not just me, were inspired to do something for the community. You want to engage the academic community in solving problems of interest to the industry. And yet, by 2018, at least at that time, there was a clear lack of suitable data sets. So there's a seminal data set called Kitty that was released in 2010, 2011, right? And it brought about a lot of the early advances in, say, 3D perception and some other fields. But by 2018, that data set was really small. And so the type of work you end up doing really was not representative of the modeling that actually is needed. Because and I experienced it myself because I wrote 2 papers on Kitty, and it was extremely painful because you have so little data. It skews the outcomes of the research. It forces you to develop models that are just good with little data. It forces you to work on, fighting overfitting, like models that have maybe too much structure in them compared to just learning things. It biases the outcome. It's too small, right? And so we were inspired to do a high quality, diverse data set with many possible types of labels, with many sensors, right? But Kitty also had many sensors. It was just small. And ours, of course, a lot higher quality, I believe. Waymo has a top class sensor hardware stack, developed since 2009, right? Like that's one of the advantages of, well, having talented people and being in the space for so long. So we felt we have something to contribute to the community, right? And so we released a data set. And what it has is it has around 2,000 sequences captured with the previous generation vehicle. And each is 20 seconds, and it contains 5 cameras, 5 lidars, of the whole scene. And it contains, and we started adding labels for all these sequences. So we added first 2D bounding boxes and 3D bounding boxes over time for all these sequences. Then we started adding 2D and 3D segmentation. Now we have actually 2D key points for all the humans, pedestrians, and cyclists, and 3D key points. We have maps that we have added. So it keeps growing. And then separately, we have a data set for behavior understanding and modeling. And that one is 100,000 sequences. And the reason we had to do this, and that one has some intermediate representation. There's a road graph and the movements of vehicles as boxes, and maybe a few other things. But there, it's hard to ship the sensor data. It's just shipping sensor data for 100,000 sequences is daunting. But you need this many to model behavior. So turns out you need a ton more data, at least temporal data, to model behavior well than perception. So in every 20 seconds snippet, you have, at 10 hertz, 20 seconds, that's 200 frames of lidar, and at least this many for the cameras. And you have maybe 100 agents in the scene at every of those. So then it's like, 20,000 times 100, that's a lot of examples of objects. And in that whole sequence, you may have one interesting interaction, if at all. So we had to go a whole other level. So we have these 2 data sets, and you can do a lot of interesting modeling, both of 3D geometry perception with the 2,000 sequences, and you can do a lot of interesting behavior modeling, because we also pick them to be interesting interactions. They're not just sampled. I mean, a lot of the sequences are boring too. So we picked interesting ones, and you can study behaviors and build models of that, right? And that's what we built, say, Sim Agents Challenge. We have a motion prediction challenge. And this year, we have 2D video semantic segmentation challenge on the perception side, where we have 5 cameras with labels in multiple frames, and now you get the same thing at test time, like can you annotate all the objects, identities, and classes. We have up to 30 classes or more. So that's one class. And also 3D pose estimation of pedestrians in complex world environments. Such data sets have not existed, no challenges. I'm not aware of this type of challenges before. So it's exciting to see what the community can do. I think what we get out of this is we focus the community on problems that are relevant to our domain. We give them data to work on this, and people develop all kinds of amazing models with this and ideas. I think we have over 1,300 citations just on the perception data set, maybe a couple hundred on the motion data set. It's more new. And we have, I think, several tens of thousands of people who are users or have looked at the data set. So it's extremely exciting, and I think we try every year to make it better. Like we complete more and more what it has, and now you can study the interplay between all these different modalities, types of labels and tasks, and how they all interrelate and enrich each other. And one other thing we did is we this year bring the two data set more in line. So now the perception data set has maps, just like our motion data set has. And we also add LiDAR for the motion data set. Um, this year we managed to compress it and add at least LiDAR. So now you also see that at least the LiDAR sensor data, in addition to the symbolic representation we give you of the scene. So it opens new possibilities to combine the two and enrich things. So I'm excited. We've been able, and I'm thankful to all the collaborators on the team. It's people do it, in a volunteer basis, on a 20%, or because it's their passion and they want to create a task we care about. They want to create a benchmark. And the purpose of these benchmarks, it shows you ultimately which ideas have merit, and it allows people across the whole world, honestly, that don't just work in autonomous driving for a lot of these, but any robotics application or even computer vision application, to compare their methods and see which ones, what the properties are, what is state of the art, right? And to me, quite a few papers published on our data have pushed the state of the art, including our own papers. And it really shows you on these tasks if you're state of the art too, if you participate, right? So it has a value.
The careful design of benchmarks is a really important, I think, boon just to the development of any field. And I think that done right, it can really push things forward well. And I guess done wrong, it can kind of leave people wondering, we've been using these for 5 years. Have we actually made any progress here? And so it's great to see Waymo pioneering some of this.
We have done our best to provide high quality data and also suitable metrics, right? So in a lot of areas, we have introduced new metrics, so variants of the metrics people use, and hopefully that helps as well.
I think this is a good place for a final question. At a very broad level, I'm curious, as somebody who's been really kind of deep in the field, how you view some of the present opportunities and kind of biggest challenges for self driving right now, and kind of what you see looking forward.
So to me, we're in an extremely exciting time, at least as Waymo. I can tell you the three-sentence history. We launched Waymo 1 in Phoenix, in Chandler, East Valley, a few years back, right? And we have been doing driverless operations there ever since. We started our first autonomous driving in San Francisco, March of last year. And we also started doing downtown Phoenix late last year. And at this point, we are out there. We have given tens of thousands of fully autonomous rides. One can just go to Phoenix, including right to the airport, all of downtown, and just order a Waymo and drive. In San Francisco, we still have a wait list, but people are riding, and I have been many times in the car. We can go pretty much the vast majority of San Francisco at all times of day and night. And we are giving a lot of customers rides. Overall, I'd say thousands of customer rides a week. So it is not like a few years ago, it was a question of can we prove we can do it? Now we're in the stage of trying to scale this and bring this as many places as possible. We also started doing autonomous driving in Los Angeles very recently. We did that first. And can we scale it, and can we make a business out of it, right? Like we want to have the right margins and deliver people, and of course have good revenue as a result, and ideally profit from all these rides, right? So now we're optimizing the experience for everybody. We want to grow, right? And so we're in the scaling phase, and it is very exciting. And there's still a lot of challenges to overcome to have it, in a lot more cities. And again, machine learning keeps remaining a key tool for this, and I can't be more excited about my job. It's the most fun job I've ever had. So.
Well, thank you so much for taking the time to chat with me today, Drago. I think this was a really interesting peek into the field, and I appreciated your perspectives.
Thank you. Thank you for having me. A pleasure to talk to you.
And that is a wrap, my friends. As I mentioned at the start of the episode, you can subscribe to The Gradient on Substack to receive not just this podcast, but also our articles and newsletters directly to your email. You can also visit us at thegradient.pub, where you'll find all of that, as well as more information about The Gradient and how you could even contribute if you're interested. And finally, if you enjoyed this episode, we would really appreciate your feedback. If you'd like to leave a comment or review, we'd love to know how we can make this series more interesting and informative to you. And with all that, I'll leave you until the next episode.